what would you do? What would we all do if the water stopped right now? If there was no water in this place, there was no water in the taps, all the bottled water was gone. What would we do to get water? What would happen? What would happen in the next hour, or the next 5 hours, or the next 3 days? What if people did not bring water in? What would we do?
Emerging Science is a Vermont Public Television production in partnership with and funded by Vermont NSF EPSCoR. EPSCoR, supporting science and engineering in Vermont colleges and businesses and encouraging young Vermonters to seek careers in science.
Hi, I'm Amy Seidel, and welcome to Emerging Science. One of the fundamental challenges humanity currently faces is preserving and ensuring a supply of fresh water. With ever-increasing human demands and fluctuating precipitation due to climate change, understanding our water systems has never been more critical. In the face of these challenges, scientists from around the U.S. assembled in Vermont to present specific challenges, exchange ideas, and form partnerships to reveal global solutions to some very local problems, all associated with fresh water.
Water interacts with everything. Water connects the physical and living environment. Water is highly engineered by humans. It's critical for human society, for economic development, for agricultural development. Water touches everything.
Water will be viewed in the future in a different way than it is viewed today. Water is not cheap and will not be cheap in those times. And also, various programs for water banking will be developed. Already we see quite a bit of that in California, especially Southern California.
I say we've got 4 basic problems with water. Too much, that's flooding. Too little, that's drought and water supply. It's dirty, water quality, and environmental issues, fish and wildlife and maintaining aquatic ecosystems.
First, let's take a look at a few of the diverse water issues around the United States.
I'm David Maidment. I'm the director of the Center for Research in Water Resources of the University of Texas at Austin. And so I have some interesting times in exotic places like the cafeteria of the middle school in Sinton, Texas, where you walk in the room and you look around and you think, whoa, we are going to take some heat here, because they simply don't want to be reminded of the fact that all this animals that they got spread around in the watershed lead to bacterial contamination in the water. For example, I'm involved in a total maximum daily load project in South Texas in a basin that has 100,000 cows. And the people who own those 100,000 cows are not too keen on the notion that they're causing a water pollution problem. And they come from the agricultural community, which is not accustomed to being regulated. The largest source of impairment on the rivers of the nation is bacterial contamination. So why don't I drink the water in this stream? Well, I don't drink the water in that stream because there's bacteria in there that could give me a nasty disease, not because it's got high levels of chemicals generally. So we think of sort of pollution in terms of like industries putting chemicals in water, and that's true to some degree, but to a larger degree it's the existence of bacterial contamination that makes natural waters threatening to humans.
My name's Tom Pihota. I've been at the University of Nevada, Las Vegas for 9.5 years. We're in an urban environment. We are Las Vegas and we're known for our excesses. Can we make better use of our water, stretch our water supply even further? That's a big challenge for the community right now, and I think they've really put effort into people tearing out grass, paying people to tear out their grass, put in appropriate landscape that reflects you living in a desert. These reservoirs were really originally built for flood control purposes. Now they're very much used for water supply. It actually comes from the Rocky Mountains. The Colorado River is where Las Vegas gets most of their water from, about 85 to 95% of it. Potentially looking for other water sources, whether that's in the state. They're talking actively about piping water down from the central part of the state, from groundwater basins, down to Las Vegas. Obviously that's very controversial because that impacts those communities that you're taking water from. Everything's pretty much on the table, including desalinization of water and trading water with adjacent states such as California, Arizona, Mexico even. You know, this is an international basin, so there's opportunities there also to work with your international partners.
I'm Costa Georgiakakos. I come from the Hydrologic Research Center. It's in San Diego, California. When I talk about water management, I talk about management in scales from 1 hour to, say, several months. In California, that's feasible because we have the natural storage of snow. Now, with climatic changes, one aspect of the change is that snow will tend to melt earlier, and that, of course, water will be lost for conservation. And, of course, the second issue in California is the demand change.
In Hawaii, we see a couple of things that primarily are influencing the natural systems, including water and including the terrestrial ecology. One is global warming, and the other is species invasion, both plants and animals. We have good reason to believe that many of the alien tree species, which have evolved in different climates, are actually better adapted to these higher temperatures. It's possible that as conditions warm, these species invasions will accelerate. At the same time, we found that these invading trees have negative consequences for our water processes. They use more water, they evaporate more water to the atmosphere, and in so doing, take away water from groundwater, which is our primary source of drinking water and water for irrigation.
Alaska is such a huge state, so we span many ecological zones. In some parts of Alaska, water is plentiful. As you start moving north into the interior and then up into the high Arctic, it's arid to semi-arid, so it's actually a cold desert. We have a balance between what we would consider domestic or individual community use of water, and then what we would consider more industrial or commercial minerals, oil and gas, natural resources. All these things require water.
In Arkansas, we're a water-rich state. We have a lot of canoeable, swimmable, kayakable rivers. We have big rivers like the Mississippi and the Arkansas, and they really propel our agriculture. We're #1 in rice production in the world.
A large percentage of our economy is based on the agriculture industry. As the supplies of water have diminished, the wells and the pumping and all of that's involved in irrigation have reduced the water table, and we see our water table dropping, and it's not only affecting the use of the land, but it's also causing the agriculture to be more expensive to produce.
We also have a burgeoning gas exploration industry in our Fayetteville shale formations, and so they use a lot of water to explore for natural gas.
Waters of the earth are constantly in circulation. Compared to the water that's flowing on the earth, the water in the atmosphere is a vast river. There's a Mississippi flowing in the atmosphere.
Modeling and predicting human impacts on aquatic systems is far beyond simple cause and effect scenarios. Elements of the water system are numerous. They include human activities, atmospheric cycles, and geologic events, all with their own sets of behavior. No one element can be used to predict overall system outcome. This is, by definition, a complex system.
Where you recognize that a system comprises many interacting entities. Those entities could be molecules, they could be people, they can be animate or inanimate, which are interacting with each other based on local rules of interaction, which may be adaptive and continually changing, but they're not necessarily subject to some kind of global control or direction.
Lake Champlain is a really unique lake in that if you look at the sort of blue stripe of the lake down the middle of its basin, there's 19 times as much land area as there is water area in the whole Lake Champlain Basin. And what that means is that when it rains, 19 times as much rain is falling on the surrounding landscape as is falling directly into the lake. The lake is an absolute wonderful indicator of our behavior overall. The lake reflects the whole watershed that drains down to it.
So it's a very, very complex system, and you can imagine looking at a variety of different aspects of that.
The emergent behavior that we're interested here are these algae blooms. So how do these factors come together? How do they interact to produce the algae bloom? Can we develop computer tools that help us answer some of those questions?
And so a part of what our complex system effort is about is in developing the tools that will allow us to expose that complexity, to understand those feedbacks, to understand those so-called emergent properties.
Within complex systems, we often talk about intelligent agents, things which are reacting to their local environment without global knowledge. And for example, it could be even something like a rock which is rolling down a stream.
There are interactions, there are feedbacks, there are loops that we don't fully understand.
The way we're going about trying to tackle this complex systems problem is first and foremost to recognize that one person can't do it. We've brought together people who are experts on stream dynamics and on biology of streams. We have brought in people who are computer modelers, and we've brought in people like myself who are familiar with statistics and fairly good at statistics.
We're now speaking the same language, so the computer scientists have a good idea about what the biologists know about the problem and what they don't know. And my contribution to the group is to try and develop computer tools or develop computer programs that can help us understand why these problems are occurring. What are these mathematical building blocks?
We try and use principles from biological evolution and apply those to solving problems on the computer. So if you think about it, biology has just done an amazing job of creating optimizations. Animals are evolving continually, generation over generation, in response to different changes in their environment, changes with each other, their interactions. What we try and do is use some of those principles when we're writing computer programs.
There really is a magic in this world, that the world is not something that we can take it into little parts and understand it and put it back together. And one of the things which I really love about complex systems is that it's really made me appreciate that magic is real, that there really is a part of the world which we are not going to understand by breaking it into little tiny pieces.